So we mentioned that there were stationary points. And we said by definition, that's when the first derivative is equal to 0. And we thought about this a bit last week, and we said, well, there were 3 types. What were the 3 types? Can you list one, Paris? Janelle, can you help her out? What's one type?
Maximum.
Right. Now, if we're being more picky, we would use the term local maximum. Now, I didn't really get into that last week, and we won't really need to worry about that right now, but I'm just adding them in. So it's called a local maximum. Paris, do you have a second one?
Minimum.
And a third one? The one that's quite a bit of a mouthful is called a horizontal point of inflection. We'll talk more about them today, hopefully. All right. Now, a maximum looks something like this. A minimum will look something like this. A horizontal point of inflection will look something like this, with, of course, a horizontal tangent. There is the other option, and it will look something like this. And basically think of them as what happens to x cubed as x when x equals 0. You guys have used the term turning points before, and that would apply to these two. These are turning points. So stationary points could be turning points if it's a local maximum or minimum, but not all stationary points are turning points. Horizontal points of inflection like this, they don't turn. So they're not an extreme point. They haven't turned. They're just a horizontal point of inflection. And as all of them are stationary points, and as you can see from the graph, they all have horizontal tangents, and that means their first derivatives are all 0. Now, last week we said we need to tell how to differentiate between them. And we went through one particular method. Janelle, which method did we go through?
What method again?
Yeah, which method did we go through to work out if it's a maximum or minimum?
How do you name that method?
Okay, so you can either call it a table of values or you can call it sort of a sign diagram. It's all very similar.
Yeah.
So I'll just call it table of values here. So essentially, we subbed in values into the first derivative. And then we kind of consider the shape. So for the first derivative at x, at a was 0, and then you did to the right of a and to the left of a. And then depending on, for example, if this was positive, 0, negative, that would then imply something like this, which would imply a max. And of course, if the reverse happened, and I'll just do it in a different color here, if we had negative, 0, positive, that would imply something like this, which would imply minimum. And of course, if it's positive, 0, positive, or negative, 0, negative, then it would imply a horizontal point of inflection. Make sense? Happy with all of that? All right, great. So now we'll start talking about something we were going into last week. We had a function which we'll label fx. Now, if you derive it, what do you get? If you take any function and you derive it, what will you end up with?
Another function.
You will get another function, and what do we call this function?
Derivative.
Right, we do call it the derivative of the function, and we'll give it this label f dash x. Now, because it is a function, as Paris has noted, can we derive it again?
Yes.
Yeah, we could. And since we can derive it again, what will we call this function?
Second derivative.
Right. So to sort of differentiate between this function and this function, remember all of these are functions, then you're just going to call this function, you derive it, you'll get what's called the first derivative. And then you derive it again, and you'll get the second derivative of the original function. And we'll use it f double dash x. And of course, this can keep going, but we're not going to really bother for our purposes here. Now, this is just analogous to, if you've got someone, if you have a woman, and at some point in her lifetime, she has a daughter, well, that daughter will also be a person and woman, and they can also have a daughter. Now, so if you've got a person who has a daughter, then, what's the relationship between this person and that person? What would you call this person in relation to that person? So if you have a person, they have a daughter, then this person would be the daughter, right? Nothing overly complicated. But if this daughter had another daughter, then what would this person be relative to this person?
Granddaughter.
Right. And we could keep going, and you could have like great-granddaughter and great-great-granddaughter. But essentially, you need to understand that all of these things here, they're still people. And who is the daughter, who is the mother, who is the granddaughter, who is the grandmother, and so on, depends who you're picking. So the term first derivative doesn't really make any sense unless you understand you're talking about the first derivative of a particular function, fx. Because if you're concerned about this function, then this would be the first derivative. Does that make sense?
Yeah.
Good. All right. Now we'll briefly review just what we said earlier. I'll just quickly write it down here. But the first derivative represents the gradient of the tangent. That's what it means, because it's the rate of change of fx, the y as x changes. And therefore, if you're looking at the term increasing, you're talking about the first derivative, and that's the first derivative is positive. If you're looking at the term decreasing, then it's the first derivative being negative. And if you're looking at the term stationary, Paris, what does that mean?
Equals to 0.
Right, it's equal to 0. Very good. And so remember, the first derivative ultimately represents the gradient of the tangent to the curve at a point. That's what it means. And then depending on whether it's positive, negative, or equal to 0, we have different terms for that. Now, if a derivative ultimately represents the rate of change of the top as the bottom changes, how do we get the second derivative?
You derive it from the first derivative.
Right. The second derivative, if you like, is the derivative of the first derivative. And so again, what does this mean then?
The gradient of the tangent to the first derivative.
Well, that's the first derivative. So we're saying it's the derivative of the gradient of the tangent. Oh, right. You were saying gradient of the tangent of the first derivative. Yeah, you could, except we haven't drawn out the first derivative. And I'm more interested in trying to work out what the relationship is to the function. So you're not wrong. You're right. But I'm trying to kind of work out this relationship. So not so much this relationship directly. I'm ultimately trying to get to this relationship. So it is the derivative of the gradient of the tangent to fx. And so how could we interpret that? What does the derivative represent?
The gradient.
And true, but try to think more fundamentally. Why is it the gradient?
Because it's the rate of change.
Yeah, it's the rate of change of the function as x changes, right?
Yeah.
So here, when you're taking the derivative of this, what are we saying? How would you interpret that? Using words. If the first derivative is the rate of change of the function, then the second derivative is the
Rate of change of the first derivative.
right. It's the rate of change of the first derivative. And what is the first derivative?
The rate of change of the function.
Oh, it is. It is correctly that. But let's now replace the first derivative with what it means graphically. What does the first derivative mean graphically?
The gradient.
Exactly. So it's the rate of change of the gradient to the curve. You know, gradient of fx. So it's the rate of change, not of fx now, but it's the rate of change of the gradient of fx. Does that make sense?
Yep.
Now, we went through this a little bit last week. Do you guys remember what the secondary they would therefore mean of the function? Or not really clear on that right now? It's okay if you're not clear because that's the main focus of today and we briefly covered it last week. But I'm just trying to think, see if you guys remember this part and if you're clear on it. Not so clear?
Yeah.
All right, no problem. So remember, we're now fundamentally going to be focusing on the second derivative. And we know that it means it's the rate of change of the gradient of the tangent. So let us now consider situations where the second derivative is positive. So what that means is that the rate of change of the gradient is positive. Right? You agree with that?
Yes. Yeah.
Now, if the rate of change of something is positive, is there a word that I could use that that makes sense to simply say, therefore, the gradient is what? What word would go in there?
Positive.
So Paris says positive. Now do you agree with that, Janelle, or no?
Yes, agree.
So does it have to be positive?
Oh, it's increasing.
Right. So the other word is increasing, and that's the right one. But let's think about this firstly. Does it have to be positive?
No.
No, right? This is actually wrong. So remember, we never said the gradient is positive. We simply said that the rate of change of the gradient is positive. So the rate of change is positive, right? But we didn't say that the gradient itself is positive. And that's my question here now. Do you see the difference? So for example, let's just use numbers here. If I have something like if I have a sequence -5, -4, minus 3, minus 2. Are the numbers getting bigger?
Yes.
Right. So what's the rate of change of the number? What's happening to them?
+1.
So in the terms of defining numbers with positive and negative, these are kind of getting bigger, right? But are these numbers positive?
No.
They're not. So firstly, just because it's increasing doesn't mean I can say they're positive. They could very well be negative. Right? Now, if I continue on with a increasing thing, if I just increase, am I guaranteed that it will always be positive at some point in the future?
Yes.
So Paris says yes. Janelle, what do you think?
Also?
You think it's yes also? Now, I said it's increasing, right? But did I have to, does it have to increase at the same rate? I mean, I could make it increase faster like this, right? So this is increasing. So this is increasing, right?
Yes.
Minus 10, minus 9, minus 7, minus 4, 0. This is increasing. And in fact, the rate, I mean, it's just increasing. So as long as these are positive, then it's increasing. But the rate, no one ever said had to stay the same. So I've got one that's increasing sort of faster, but I could also make it increase slower. So I could have negative 10, negative 9, negative 8.5, negative 8.4, negative 8.35, negative 8.33. So is this increasing?
Yes.
Now, do you think it will become positive?
No.
Right? No one ever said it had to become positive. I mean, maybe you don't think that's a clear enough example, so maybe I could go negative 2, I could go negative 1, I could go negative 1/2, negative 1/4, negative 1/8. I mean, this is probably clearer to you. But you can see that the numbers are getting bigger, right? I mean, there's no doubt that they're getting bigger. But will that mean it will become positive?
No.
No. So just because something is increasing does not mean it will become positive. And you need to separate the concepts, right? One is talking about the value, that's whether it's positive or negative. One is talking about the rate of change. Are we clear on that?
Yes.
All right. So therefore, if the second derivative is positive, that means the derivative of the first derivative is positive, which means that the rate of change of the first derivative is positive, which therefore means the rate of change of the gradient to fx is positive, which is another way to say that the gradient is increasing, because we've said it before. If the first derivative is positive, that means it's increasing. And as a result, since the second derivative is positive, it's the first derivative of the first derivative, which means that the gradient is increasing. Clear on that? So that's true. But now I want to go further and think of not just say that the second derivative being positive means that the first derivative of the first derivative is positive, which means that the first derivative is increasing, which it is. But now I've got this link worked out. I want to work out what the link is to the function. All right. So if my gradient is increasing, let's just imagine I've, just like earlier with numbers, I wrote out some numbers and made them bigger. Let's imagine I just had some sort of gradient, right? So let's add a gradient like that. What sort of number, if roughly, Janelle, if I had a gradient like that, is it positive or negative? Give me a number.
-4.
All right, let's say it's -4. Let's make it a bit bigger. It's increasing. So give me a number that's, from -4, let's increase it. What number do we have?
-3.
All right. And if you draw a -3, it'll kind of look maybe something like this, right? We won't talk about whether it's to scale or not. We're not really interested in the to scale. We're more interested in the concept. So let's say it's something like that. And then keep going. What's another number?
-2.
All right. So you might have something like -2. And then, these aren't actually -2s anymore, but, and so you can see that the gradient will just change, right? And then at some point you might reach 0, right? And what happens after you reach 0? If it's increasing, it will
be positive, the gradient.
Right. So you'll get something like this happening, right? Which means your curve might potentially have a shape that kind of looks like this. All right, that's one option. Now, no one's ever said you had to start with a negative number. You could have started with a positive number. So if you start with a positive number, you probably would have just got something like this. And that means your curve would have looked something like this. You could also not necessarily, as we mentioned earlier, go positive. It might just get more and more positive, but not actually become positive. So you could have something like this, starting negative and becoming increasingly positive, but never actually being positive. So you could have a curve that might look something like this. Does that make sense? And so if I'm giving you examples of these sort of curves, then a curve that might look something like the one we've got on the left here might be something like y equals x squared. And something like the one in the middle might be something like, might be something like y equals, an exponential function. And something like the one that we've got on the right there might be part of the hyperbola function as an example. So this here might be y equals x squared or similar. This here might be an exponential function or similar. And this here might be just the right-hand side of a hyperbola. Can you see how these are all examples of those situations? Does that make sense? And all of these represent situations where the second derivative is positive. Now, if you compare these situations and think about what we got from them, can you see any similarities? Can you see what these would represent, what the second derivative would represent about the function? Not clear? Well, not a problem. If you're not clear about it, let's take a look at the opposite situation. Oh, that scaling didn't work out too well. Never mind. You guys get the idea. All right, let's look at the opposite idea. If you've got a second derivative being negative now, what does that mean?
The gradient is decreasing.
Right, you've got a decreasing gradient. So doing something similar to before, we could potentially have a really, really positive gradient like this, but it will get lower in value, which means graphically it will do something like this, and then it could go negative. So it might, do something like that. On the other hand, it could simply, start fairly flat. It could start negative even and just become more negative. And it could also, of course, do, well, anything sort of in between, really. Wait, did I have that right? No, that one's wrong, by the way. Oh, no, that one is correct. Negative, and then becoming that. So, yeah, I mean, those are really the main types, I guess. The other type that might be worth showing you is basically if it's like this. So if it starts really positive and it does become more negative, but it never reaches 0. That will give you graphs like this. And so this would be something perhaps like negative x squared. That would perhaps be something like, you could think of this as the hyperbola one, for example. So the left-hand side of 1 equals 1 over x. And this one you can perhaps think of as log x. As an example. Oops. If this is one example, so it could be a hyperbola as well. But if I'm saying log x, then it would look more like this. But both of those fit my situation here. All right. So can you guys tell the difference between a curve, a function that has a second derivative being positive and a second derivative being negative? So these are second derivatives being positive. And these are second derivatives being negative. Do you guys notice a difference?
Isn't it the same as first derivative?
No, it isn't.
What?
So the first derivative is regarding the gradient itself, right? So here, for example, the gradient here is negative and the gradient here is positive, right? Agreed?
Yeah.
So at one point, the gradient is negative on the left. At one point, the gradient is positive on the right. Now, but we're saying that the second derivative is positive the entire time. So we're trying to figure out what the second derivative represents. Does that make sense?
So is the blue line the first derivative?
Well, the blue line is meant to be the function, and the green lines are meant to be tangents to the blue line. So we're trying to work out from gradients what the function looks like. And we got these kind of examples.
Okay.
And then I just gave you specific examples which would kind of match those. Both for second derivative being positive and for second derivative being negative over here. And so what's the difference between a second derivative being positive and the second derivative being negative? So while you guys think about it, I'll just put them all on the same page. So I'll just give you examples. They'll be the same thing as before, but I'll just put them on the same page so it might be easier to spot. So we're trying to find something to distinguish between, the top three and the bottom three. Now we know from drawing it out that the top three are second derivative is positive for the whole curve. The bottom three are the second derivative is negative throughout the whole curve. And we've suggested as examples, this is y equals x squared, and this will be y equals negative x squared. This could be, y equals some sort of exponential function as an example. This could be the negative version of that, potentially. This could be something like y equals 1 over x. This could be something like, log x, potentially. It could be anything, really. It could also be, negative 1 over x. That's all depending on exactly, but the right sort of shape. We're looking at the sort of the shape. Can you see the difference between the top three and the bottom three? What the second derivative would decide?
When it's bigger than 0, it concaves up.
Yep.
And smaller than 0 concaves down.
Correct. So, and we have done this last week, but I know you guys aren't familiar with it. So that means this is concave up and this is concave down. Are we clear on that? Can you all see that? Janelle, are you happy with that?
Yeah.
Yep, so indeed, that's correct. That means the second derivative determines whether it's concave up or concave down. If it's positive, it's concave up. If it's negative, it's concave down. And I want to be perfectly clear, that is not the same thing as increasing or decreasing. So for example, this is concave up, but is this increasing or decreasing?
Increasing.
Right, this one is increasing. Is this one increasing or decreasing?
Decreasing.
Which one?
Decreasing. Oh wait. Increasing.
I or D? You're breaking up a lot, so.
Oh, increase.
Well, take a look, right? First derivative, it's the gradient of the tangent. Is the gradient going up or down?
Go up.
How is the gradient going up?
Oh, isn't it becoming less negative?
Well, but we're asking about the function. Is the function increasing or decreasing?
Decreasing.
Yeah, the function is decreasing, but do you understand that, Janelle? When we're asking about the function, we're not asking about the gradient right now. We're not asking what happens to the gradient, which of course is increasing because that's the definition, right? We're asking what is the gradient now? And the gradient is negative, which means the function is decreasing. So to be perfect, if it's not clear enough, let me just add that here in particular. We're saying this is a concave up function, but the function is increasing in this example here. And in this example here, the function, not the gradient, my question is not about the gradient, but the function is decreasing. Are we clear on that?
Yeah.
And here is the function increasing or decreasing?
Decreasing.
It's decreasing. And here is my function increasing or decreasing?
Increasing?
Right. So students get these mixed up all the time, but it's actually really, really clear. Firstly, you need to remember increasing, decreasing stationary points are not the same as concave up, concave down. They're just different things. You can't say concave up, so it's increasing. You don't know. Concave up could be increasing, it could be decreasing. You can't say concave down, so it's decreasing. You don't know. If it's concave down, I can give you an example. It's increasing, like here, or decreasing, like here. So there's, 4 different possibilities. Or it could be, of course, like this, where it's decreasing to start with, and then it's increasing later. But the point is, you can't just go, because it's concave up, therefore I know it's increasing or decreasing. You don't know. You can't tell, because it's concave down, whether you're increasing or decreasing. You don't know. So, just like, if someone gets a good mark, you don't know if they're going to be getting better or worse for their, for the next mark. You don't know that. You just know their mark. The two things aren't necessarily related. Okay? Ignoring exceptions like getting 100 so you can't get better, ignoring exceptions like that because, we have analogies aren't perfect. The point is, if I tell you someone got 90%, you have no idea if they're improving or they're, getting worse at that subject. The two concepts aren't the same. Just like function value and gradient aren't the same thing. So here we've stressed that the first derivative tells you the gradient of the tangent. And then specific cases, like when it's positive, means it's increasing. That's the function. When it's negative, we're saying the function is decreasing. And when it's 0, we're saying the function is stationary. Now remember, the second derivative had specific cases. The specific cases was concave up. Is the second derivative is positive. Concave down. Is the second derivative is negative. So what do you think the second derivative represents? If the first derivative represents the gradient of the tangent to the curve, what do you think the second derivative represents? Given that it will either be concave up or concave down.
Concavity.
Exactly. So if it's not clear enough, let me repeat that and just make sure that you guys really, really understand this because it's important. First derivative of a function represents the gradient of the tangent to the function. That's what it means. The second derivative, shortcutting, represents the concavity of the function. And yes, we've talked about y because it's the gradient of, it's the rate of change of the gradient, which then becomes concavity. Both gradient and concavity have special cases that we use special terms to describe. Those are increasing, decreasing, and stationary. These three terms are first derivative only. Don't ever think about the second derivative when you're using these terms to describe the function. These three terms are first derivative. If you're talking about first derivative being positive, that means increasing. If you talk about the first derivative being negative, that means decreasing. If you're talking about the first derivative equal to 0, that means stationary. And vice versa. If you're saying increasing, that means first derivative is greater than 0, and so forth. The two things mean the same thing. And if you're ever asked questions about concavity, then you should be heading for the second derivative. You shouldn't care about the first derivative when you're talking about concavity. You shouldn't care about the second derivative when you're talking about the gradient of the tangent. Does that make sense?